Yeah.
I want to remind you guys something. As we get into polar coordinates, remember you can go on your calculator, hit mode, put in the polar coordinates right here. Bam. And then if you go to y equals, it'll actually be r equals. And if you put in there a function maybe like this, you'll end up getting it's amazing. We call that the butterfly curve because we're remarkably creative people. Might be. Anyway, so that's kind of nifty. Some of you guys are actually showing me examples of sometimes back in pre-calc you do things where you have you figure out functions to create faces on the screen or to create some kind of shape on the screen. So some of you guys might have done that before also. All right. But obviously you can put in there simpler things just to get an idea of what things look like. It'll help you out a bit. All right. Let's go back to this guy here. Turn him on. Sweet. And just to point something out, if I divide these two, if I take the y divided by the x, don't the r's cancel, and sine divided by cosine is tangent, so I mean that's where that comes from. Blah, blah, blah. And of course this is go there, right there, blah, blah. Okay. Plus it's the identity from trig. So these conversions should not be too bad. Obviously, if I ask you to do something like this, I'm going to want the exact value. When I give you an angle, that's something you should know. All right? So here the x would be twice the cosine of 5 pi over 3. And 5 pi over 3 is in the what quadrant? Fourth quadrant. I like it. So cosine is going to be positive. I like it. And again, I don't know if I've had a chance to say this, but I wish that we would let go of SOHCAHTOA and just realize it's no good. And I know if you love SOHCAHTOA and you hate me already, you have a little more reason to hate me. But the reason I say that is because it's so much easier to remember values for sine and cosine if you remember that cosine likes x. So the further I get away from the x-axis, the smaller cosine gets. So here I want the cosine of 60 degrees. Okay, that's far away from the x-axis, so it's going to be the smaller one half. Sine of 60 is closer to the y. Sine likes y, so sine is going to be biggest at the y-axis, 90 degrees or 3 pi over 2. So this will be 2 times 1 half. So you get 1, and the y piece will be twice 3 over 2. It's in the fourth quadrant, so sine is going to be negative. So that just becomes negative rad 3. So the point will be 1 negative rad 3. Cool, I like it. Not too bad. Same thing here. The x piece will be negative 12 times cosine of this, and that's going to be in the third quadrant. So cosine is going to be negative. So it'll be 12 times cosine of 30. Good. So it'll be 6 rad 3. Is that cool? So it'll be 6 rad 3. And then sine is also going to be negative down there. So it'll be 12 times sine of 30. 1 half. So that'll be 6. I like that. Not too bad. Now where we desperately need help, and of course the part that's going to be more immediately happening to us is this kind of stuff here. These conversions. These function conversions. But you start to realize what you're looking for. So if only there was an r in front of that sign, I don't want to put square root of x squared plus y squared, and then sine would be what? I mean, so if only there was an r in front of it, so of course I just give both sides of the equation another r. So I multiply by r, and then I get x squared plus y squared equals 5y. And you could, if you wanted to, you could subtract that over, complete the square. It would, of course, become a circle with the center moved. I like it. Is that decent? So I don't know if you remember, r equals something sine theta is a circle that's sitting on that's been moved up on the y-axis. R equals cosine, something cosine theta is one that's been moved over on the x-axis. Kind of makes sense. Sine's y, cosine's x. I like it. This guy I put in there to see who realized. And it also comes out with something kind of nifty. If I take a tangent of both sides, it agrees with one of my conversions. So if I take a tangent of both sides, what's the tangent of 30 degrees?
3 over 3.
Yeah, exactly. Rad 3 over 3. I like it. So then that tangent theta is y over x, so I get y equals rad 3 over 3x. So the rad 3 over 3, which is the value of tangent, is the slope of the line. Tangent line. That's part of where we came up with it. It's crazy. Again, we're very creative people. Alright, how's that? Is that cool? So you can consider these tricks, but what you're really trying to do is to take what it is and match it up with some conversion that you know. Sometimes you're going to have to put in there rad x squared plus y squared. There's no other way around it, so too bad. But thankfully these I didn't make them too ugly. Oh, you're here?
Yeah, wouldn't that just be y is equal to root 3 and x is equal to is that that?
So this is converting to a function.
Yeah.
It's not a point, right?
Yeah, when you rationalize it to I'm just going to do myself.
Alright, okay. Good. This guy kind of sucks. R secant doesn't mean a damn thing, so I don't want to multiply both sides by R. But secant theta is
1 over cosine.
1 over cosine. So if I just pull that cosine part up, now this is
X.
x. So x equals 3. So if you plug this in your calculator, it's just going to draw a vertical line. I like it. Okay. Alright. So what about down here? Now here's where you got to be careful when you do inverse tangent. You got to remember what quadrant you're in, so you do the correct reference angle stuff. All right, this first one's nice because I gave you the first quadrant. So what do I need? I need r and theta. R is easy enough. How do I get r?
Square root of x squared plus y squared.
Yeah. So it'll be 3 plus 1. 4 square root is 2. That's crazy. And then how do I get theta?
Arc tangent of y over x.
Yeah, y over x. I like it. So 1 over rad 3.
Pi
What's that going to be?
Pi over 6.
Pi over
6.
Yep. So what you guys said? Pi over 6. I like it. So now I got 2 pi over 6. I like it because I'm in the first quadrant, so I don't have to adjust that angle. What about this guy? He's going to be in the second quadrant. I like it. R is just going to be it's really 1 over rad 2, 1 over rad 2. So it's 1/2 plus 1/2 is 1. Square root of 1 is 1. So R is 1. And you can also realize it's on the freaking unit circle. So of course R is 1. Get out of there. Rah. And then theta, yeah, it's going to be some kind of 45 degrees. Since I'm in the second quadrant, it's going to be
90 plus
3 pi, 2 pi over 4.
3 pi over 4. So then I get 1, 3 pi over 4. Kick ass. So what about these here?
Which you just replace x's and y's.
Yeah, so this first one, there's really not too much you can do. Y is r sine, x is r cosine. If you did pull those up, you could at least write r squared sine 2 theta over 2 if you wanted to, equals 1. Because remember, sine theta, cosine theta is half of sine 2 theta. Oh shit. Sine 2 theta is 2 sine theta, cosine theta. You're going to want those trig functions at your fingertips. Those trig identities. If you didn't do that, it's okay. Don't freak out. This one, I would much rather, do you see if I foil this bad boy out? then this part is r squared minus twice r sine theta. Oh, it's going to be 4y then. Plus 3 equals 0, or however you want to say this. R squared minus 4 r sine theta plus 3, or is that cool? You could just put r cosine theta there and r sine theta there, but that's sort of weak. Yeah? Alright, so what about this guy here? What's a good first step there?
Just turn that again.
The y over.
Yeah, x squared plus y squared equals y over x, so you get r squared equals tangent theta. That's a neat one to graph. Now, if you want to graph this in your calculator, you're going to have to do...
Plus and minus 2.
Yeah. I like it. Yes, ma'am. Where are we at? Oh, for this year? Yes, totally. I was going to say something here about this, but I didn't want to spend too much time. You could always write this in truly an infinite number of ways, but sort of not really infinite. It would just be, I could have a positive one or a negative one. I would just have to make sure the angle kind of agrees. So I could say negative 1, negative pi over 4. I could say negative 1, 7 pi over 4, right? Do you guys see what I'm saying? So if I could tell somebody, so remember, polar coordinates is all about, instead of saying to somebody, go this much this way and this much that way, it says, turn this angle and then go this far. That's what polar is all about. So I could tell somebody to turn the wrong way and then walk backwards. So that's what her question was. I could have them turn the opposite angle from this. As long as I tell them to take a step back, they're going to end up at the same damn point. So you see that kind of stuff happening down here for plotting the points. Oh, I like this here too. Obviously, I put this on here. This is new for this handout. If you've seen this handout from me before, this is related, of course, to what we're going to be doing with integration across polar coordinates. This is going to be what the region might look like that I'm working with. So this region, if I drew it out, it goes from r equal to 2. So you guys remember how to work with this? This is r equal to 1, 2, 3, 4, and I made the blue line 5, so it's easier to kind of count, possibly a little bit. So from r equal to 2 to r equal to 4, and theta goes from pi over 4 to pi over 2. So it's just going to be this guy. I like it. This is what we actually call a polar rectangle. And you can argue, star rectangles are, everything in polar is all about curving around, right? So this is what we call a polar rectangle. And we're going to build what integration looks like in polar coordinates by analyzing what the area of one of these, a very tiny one of these rectangles would be. Is the second way we're going to do it. But very quickly, so is everybody cool with that? That's just plotting that region out from r equal to 2 to 4, and theta goes from pi over 4 to pi over 2. Yes?
So the polar's only on a 2D plane and spherical is a 3D version of this?
Polar is 2D, cylindrical is 3D direct version of this. Spherical is kind of a different kind of dude. Cylindrical is just taking exactly this and adding z in. That's all cylindrical is. Spherical is where there's multiple angles defined. I like it. Alright, and I should be able to bust through these semi-quickly, right? Let's see, 3 pi over 3, so you turn to pi over 3 and just go out 3, so I'm sitting right in the middle of my little... I like it. If I add another eyeball, it's like a little Frankenstein, but maybe just 4, 3 pi over 2. So I face 3 pi over 2 and I go out 4. It's amazing. And then this one I face. So it's kind of funny to me. I wondered why they didn't just call it theta r instead of r theta. To be honest, because theta sort of is more like the input variable, but too bad for us, we weren't around back then. So here, pi, I turn to look at pi and I go 3.5. 1, 2, 3.5. Here, I look at negative pi over 6, which is going to just be going back from pi over 6. So coming back from pi over 6, I'm going to go, what am I talking about? I'm being silly. Negative pi over 6 is here. Get ahead of myself. So this is negative pi over 6, and then I go, where am I at? Here we go. 3 halves out, so 1.5 out. Bam. Get ahead of myself. Here's the one I'm going to look at 2 pi over 3. But then I'm going to go back, so I'm going to go this way. 3. 1, 2, 3. Is that cool? So look at 2 pi over 3 and then step back away from it. And then finally I'm going to look at negative 11 pi over 12. Where's that going to be? So here's, I'm going to go back 11 pi over 12, so that's actually going to end up where?
5 over 12.
13 pi over 12. If I go back 11 pi over 12, I'm going to end up at 13 pi over 12. And then I want to go 2 in that direction. Cool. I like it. And hopefully you guys labeled yours. Unlike me. No? Alright, well that's fine. Later you'll look at it and go, alright, I did something. Yes, sir?
Why is there a blue circle in here? 5.
To be honest, it's just the best image I found a while back that actually had all the angles, and I like that they broke it up into 12 so they actually capture all of the important angles. And they just put the blue line, I think they just put it there to be the 5th one. It would have been better to have it on every other one or something. Yeah. Which one? B? As in boy?
Oh, no, that one.
Oh. Oh, D, this one. So, negative pi over 6 is going back pi over 6, right? So I'm looking here, and then I go back 1.5. I mean, not back, but I go in that direction 1.5, because, yeah, I like it. So if R is positive, you're going to go in the direction you're facing. If R is negative, you're going to go the exact opposite direction from where you're facing. Sweet. Hopefully this is familiar. This comes back to you. So the last thing I want to do before I let you out of here, we are going to set up what the polar coordinate double integral would look like. And you say, well, Jeff, that sounds so trivial. Just let us do that around. Sounds like too easy.
Yeah, that's exactly what
I know. You can feel it.
I was like, wow, that sounds.
You're like, let's just skip this section, Jeff. You want some challenges?
I was like, oh, polar coordinates, that's my specialty.
That's your jam.
Yeah.
So many.
I used to leave like
Let me see.
Really sucks.
So just to give us a little motivation about why we need polar coordinate integration, if I said, let's see, how do I say this? If I want to integrate this function over the region yeah. Ooh, I like it. So take a second and see if you can draw that region. I didn't tell you what x is doing, but these are the positive radicals. So this is an equation of what, really, truly? Circle. So the top part of the circle, the top part of that circle. So take a second and try to plot that out. Sketch the graph of that region. We'll quickly see why it so sucks. Just draw this region. Yes, sir.
slide down.
In a situation where you have that restriction where it's circular or cylindrical, that's when you want to convert it over to use that.
Yeah, there are certainly problems that I can do even if the region is circular, but it'll either be easier or possible to do if I change it to polar very often. Yeah. Just the one. Just the one. This. All right. So this, of course, is just the top part of a circle with radius 1. Yeah. And this is the top part of a circle with radius 2. Yeah. So pretend like those are half circles. I know they look more like the top part of Stewie's head, but I can't do it. Quick. So what's going to suck about this is...
Oh, never mind.
Okay, cool. So everybody cool with that? It's the top halves of the circles. One of radius 1, one of radius 2. Is that cool? I like it, I like it. So if I try to do integral, let's see, which way I want to go. It doesn't really matter. If I try to do integral dx dy of this, what's y doing?
It goes from 0 to the bigger circle, and then it goes from the circle to the circle, and then from 0 to the bigger circle again.
So y goes from 0, but what do we have to do with x? What does x do? X goes from this side to that side, but then here it goes to that side, and somehow it picks up again and goes there. I mean, that's horrific. And if you try to turn it around, you're still going to have a trouble. If you try to go this way, it's going to go from this side there, this side there, and then back to this side to there. At least that way looks a little less freaky, right? But even if you try to set that up, just to show you, I think that's the way I try to set it up here, just to show you. It would be -2 to 2. Square root of 1 minus x squared to square root of... And this is just for a piece of this. I just did this for this piece, where y goes between these two circles, right? Is that cool? I would have to still do an integral for that and an integral for that. I couldn't just do one and double it because it all depends on what the function's doing. And then inside I got this. So once I integrate this once, I'm going to get this 3xy plus 4y cubed over 3, that kind of thing. Do you guys see that? And then I'm going to plug this in there. I'm going to have this to the 3/2 power. It's going to be impossible. Yes, sir?
Couldn't you do, you could find the area between, like y goes from 0 to the big circle, right? Or not the area, but the volume above that. And then also find the one from 0 to the small circle.
Yes, and then subtract.
And then subtract.
But by setting this up, I just want to show you that you're going to end up with this truly disgusting interior of this integral, which isn't technically impossible to do, but it's close enough to impossible that I just don't want to do it. All right, so this is a little motivation as to why the kind of functions I want to look at using polar coordinates. So let me see, I might just show you. Screw it, I'm going to show you the whole thing. Just so I don't have to try to draw this, I'll show you this. So the same way that we broke up our region in 2D, right, for x, y, functions of x and y, we broke up our region in 2 dimensions into little squares, and over those would sit these rectangular solids, and we did like dA, which was equal to dx times dy. That makes total sense. So now this is why I said earlier, this polar rectangle idea. We are going to break up our region into these... Oh, scheisse, Jeff. You just had to turn it on. Alright, I'll let it warm up. We're going to break up the region into these polar rectangles. All right, now stay with me for a second. I was hoping to have this up and running. So imagine, now please realize this is a very small segment. So I can even imagine I'm talking about a piece of this, right? I just want it big enough that you can see what's going on. So let's say that this is, let me see if I can denote this well enough. This piece out here is Ri, and this piece out here is Ri minus 1. So what I'm doing, let me show you this picture. It's on page 1051. So here's my little piece of this grid. So I've taken my region that I'm integrating over. I've broken it up into all these little tiny infinitesimal parts. And for example, each one of these is a different R. So this is Ri, and this is Ri minus 1. It's that next R down. So I'm kind of like scanning over my region as my theta goes from, did they denote it here? Yeah, here's my theta j minus 1. So as theta changes, my R changes across that region. So it's exactly like as x changes, I can scan across using y or the other way around. So this is very similar to what we did before. There's going to be a major difference, though, in one piece. So what we do is we take, I need a higher an assistant. We find this middle piece, because that's the easiest piece to get for each little tiny polar rectangle. That's sort of like finding the xi when we did Riemann sums for a regular f of x back in 180. So this I'll call r star, r I star, and it's going to be equal to, it's halfway between the two radii. So it's 1/2 of Ri minus 1 plus Ri. I'm going to let that soak in. So if I just average these two, I get to the center. Okay, I like it, I like it. And then, so this area here, what is the area of a sector? So remember that. Area of a sector. Who remembers? So this will be like, something like this here. So the area of the sector. What is this arc length? Arc theta, I like it. And the area of this, the funny thing to me is, it works if you think about it as it decreases in the limit that it becomes infinitely small. But really, if you consider this to be the base and this to be the height, r, then it makes sense the area is going to be 1/2 the base times the height. And that actually is what it turns out to be. Right, it's not exactly correct for a large case, but for a small case, the limiting becomes this. But that is the area of a sector. I don't know if that looks familiar. That's the area of a sector. So then, what is this area, this little area element going to be? So it's going to be, yeah, let me make sure that, let's see, I don't want to keep turning the lights on and off. So this little area, let's see. Well, they don't put it on here. Put it on here. Oh, here we go. Okay. Yeah, the change in area from one segment to the next is going to be 1/2 Ri squared change in theta. Let me make sure that that's theta. So the area related to this radius versus this radius, let me let that sink in. So as I move out, the area changes by this much. So it's going to be what the area is up to Ri minus what the area is up to Ri minus 1. That's going to be this little area element. All right, cool. So that's going to be like, just like dx is going out x and then going out just a little bit more. So this dA is going to be this, actually, how much the area changes by as I move out a little bit more.
Can't we rewrite that?
Say again?
Can't we simplify that though?
Yeah, totally. And I'm going to use this fact to help me out a little bit. So this becomes 1/2 Ri, we can take a 1/2 delta theta out. And I get Ri squared minus Ri minus 1 squared. And then I can just factor that. So I get 1/2 Ri plus Ri minus 1, Ri minus Ri minus 1. I'm just factoring this difference of squares. Delta theta. Oh, what was this? That was that Ri, right? Ri. And this is, what's this really? This is just going to be delta R, delta theta. Now let me pull this up here. This is all in the book, but I want to make sure you understood what each piece was. So now I've got the change in area element as you move out a little bit further is equal to Ri, delta R, delta theta. Yeah. So now, just applying that same limiting idea we did back in the day when we first did Riemann sums. This means that dA